Hello, everyone. This is Yin Xiaofeng from Tsinghua University. It's my honor to speak here, and I'm very glad to share my recent research findings with you. Today, I'd like to introduce a scalable methodology for designing efficient interconnection network of chiplets. Moore's law has governed the semiconductor industry for over half a century, but it is widely observed that Moore's law is becoming hard to sustain. First, the device density approaches physical limits, and the technology development slows down. Then, the recent chip size has reached the lithographic reticle area limit. As both density and area fail to grow, the number of transistors is difficult to grow. Another reality is the cost crisis. Advanced technology means high costs, and large chips mean low yields. Therefore, the manufacturing costs increase rapidly. At the same time, the NRE costs, such as the EDA software cost and the IP cost of advanced technologies, also increases rapidly. The cost crisis is fatal to the profit-driven semiconductor industry. Chiplet architecture emerged with the maturation of advanced packaging technology. It is to build systems from multiple small chiplets. There are many advantages. First, it can break the lithographic size limit of a single chip. Then, the design cost and manufacturing yield of small chiplets are much better than that of large chips. Moreover, significant costs can be saved by reusing chiplets within a single system and between multiple systems. In general, chiplet architecture is economical and scalable. As shown in the figure, the scale of modern computing systems varies under different work scenarios. If a single chiplet can cover all scenarios, from mobile to data center, huge cost savings can be achieved. Building chiplet-based interconnection networks faces the two main challenges. One challenge is building systems at different scales with the same chiplet. 2D mesh topology is widely used in on-chip networks because it is implement-friendly. However, for large systems with thousands of cores, such as the wafer-level system, the performance of 2D mesh network is poor because the diameter is up to square root of n. There are significant differences in design approaches between large and small networks. Thus, it is challenging to develop systems of various scales based on the same chiplet. Another challenge is the routing design for multi-chiplet systems. Connecting several networks on chip together can lead to potential deadlocks and congestion problems. At the same time, the routing algorithm is closely related to the topology and scale of the system, so it is not easy to expand. Primitive approaches such as dimension order routing on 2D mesh not only limit performance and scalability, but also fail to provide adaptivity. Motivated by the challenges, we think a good chiplet interconnection scheme is supposed to have these characteristics. First, it can build multiple systems of different scales from identical chiplets. Second, each chiplet is based on a typical NOC architecture. Then, the scheme should be scalable, which means the topology is variable without changing the chiplets. Last, the routing algorithms are supposed to be deadlock-free and efficient enough. Okay, let's discuss them in detail. First, I'd like to introduce the network on the chiplet. Limited by the layout and wiring capability of the chip, most on-chip interconnection networks have a flat topology. So we adopt the most commonly used 2D mesh as the topology of the on-chip network. The microarchitecture of the router is the typical virtual channel router, which contains a few separate buffers at each input port. The switching technology of the router is based on virtual cut-through, which is widely adopted in the on-chip network. In general, our methodology makes as minimal changes as possible to the traditional NOC architecture. Okay, let's see how we can make the topology variable. Each chiplet has multiple external links. To better use these links, we adopt a method called the interface grouping to cluster the adjacent edge nodes into several groups. For all physical interfaces in a group, we treat them as a single software-defined interface and always connect it into the same size interface on another chiplet. As shown in the figure, a 6 times 6 2D mesh has 20 edge nodes, and these nodes can be clustered into 4 or 10 groups. After interface grouping, chiplets can be regarded as large nodes with flexible radixes. In this way, we can flexibly adjust the radix of the chiplet node, and the bandwidth on each edge can also be adjusted. Such grouping method is not based on hardware, but is software defined, so doesn't change the original NOC architecture. However, the software-defined grouping approach could lead to bandwidth unbalance and underutilization. Inspired by the multiple channel memory system, we propose a method called network interleaving to fully use the interface bandwidth. More details will be given later. After interface grouping, each chiplet can be regarded as a high-radix node. Therefore, chiplets can support topologies with shorter diameters. As shown in the figure, chiplets can be connected into a hypercube of 2 to the n nodes by clustering interfaces into n groups. The dimension of the n interface group grown along the edge ring, and each chiplet-to-chiplet link connects pods of the same dimension. Compared with 2D mesh, the diameter of the hypercube reduces from the square root of n to the logarithm of n, and it doesn't waste support at the edge. Another typical topology is ND mesh. As shown in the figure, chiplets can be connected into an ND mesh by clustering interface into two N groups. The dimension of the interface group grow along the edge ring. Each dimension has two directions, negative and positive. Chiplet-to-chiplet link connects the positive and negative interface of adjacent chiplets in the same dimension. As shown in the figure on the right, chiplets can also be connected into a dragonfly network of n plus 1 nodes by clustering interfaces into n groups. In addition, in addition to above homogeneous topologies, irregular topologies can also be supported, but irregular topologies are not discussed today. After introducing the interconnections, I'd like to show you the routing design. First, I will introduce some necessary concepts. A physical or virtual channel from a large label node to a smaller label node is called a minus channel. A physical or virtual channel from a smaller label node to a larger label node is called a plus channel. A physical or virtual channel connecting nodes of the same label is called an equal channel. In the figure, red arrows are minus channels, and green arrows are plus channels. Minus first routing is a routing algorithm that restricts turning to a minus channel while the current channel direction is plus. In other words, the message is delivered across a few minus hops first, and then across a few plus hops to the destination. Passes that follow the routing rule are called minus first passes. The labeling method is shown in the figure. The labels of the cores are the normal labels of the 2D mesh, and the labels of the interfaces are a ring of negatives. The general idea of designing the minus first routing algorithm is to find a minus first path for any node pair based on the labels. For example, a message needs to be delivered from node 13 of one chiplet to node 5 of another chiplet. It first goes to the interface rings through the minus path. Then it goes to the destination chiplet through the external link. Finally, it turns from the minus channel to plus channel and reaches the destination node. This path is the typical minus first pass. I'd like to present the minus first routing on Hypercube as a specific example. As shown in the figure, each of the 16 chiplets is clustered into radix 4. The routing algorithm is straightforward. Each chiplet has its coordinates in the hypercube, from which we can calculate the offset, which are the dimensions that need routing. The interface nodes of these dimensions are distributed along the interface ring, and the message can traverse all these dimensions by going around the interface ring through a minus-only path. Once the message reaches the target chiplet, the message continues along the interface ring until it can reach the destination by one turn from minus to plus. For example, if the source coordinate is 0, 0, 0, 0, 0, and the destination coordinate is 1, 1, 1, 1, 15, so the chiplet coordinate offset is 1, 1, 1, 1, which means the message needs to go through all the dimensions. It first goes from the source to the dimension 0 interface through minus channels only. Then it goes along the interface ring and traverses all dimensions through minus channel and equal channels. Last, it goes from dimension 3 interface to the destination with one term from a minus channel to a plus channel. The key is that a message can traverse all dimensions along the interface ring. For other topologies that can adopt dimension order routings, such as the ND mesh, the algorithm is similar. The algorithm is based on traditional minus first routing, but there are a few differences. To make the method scalable, each chiplet is individually labeled, and there are channels connecting nodes of the same label. This equal channel can lead to deadlocks, as shown in the figure. The dependency circle forms among the interface groups of the same label in the same dimension. Therefore, we improve method routing to solve the deadlock problem. Let's define a new concept. A equal-label group is a group of connected nodes with the same label. The two new conditions are: in the equal-label group, virtual channels are used to separate packets entering along the plus channel from other packets. And there is no deadlock in equal-label groups. The theorem is easy to prove. Suppose there is a channel dependency circle, and there is no deadlock in the equal-label group according to condition 3. At least one channel of the circle is not equal. So there must be a chain of dependency going from a plus channel to a minus channel. As turning from a plus channel directly to a minus channel is prohibited by MFR, there must be at least one equal channel in the middle of the chain, which means that the chain must go through at least one equal-label group. According to condition 2, packet entering the group along the plus channel will go to another virtual subnetwork, and according to condition 1, packets in this virtual subnetwork cannot turn to the minus channel as they leave. Therefore, the channel dependency circle cannot exist. That is, the minus first routing algorithm with the equal channel is deadlock free. As we introduced before, several interface nodes are grouped into one object interface. Since the group is software defined, a traditional message can only come out from one physical channel. This results in a significant loss of bandwidth gains from grouping. Therefore, we propose a new method called network interleaving to improve inter-chiplet communication efficiency. As shown in the figure, when the source node sends a message to the destination node on another chip, we distribute the traffic evenly across the entire abstract interface. In this way, the inter-chip communication bandwidth can be fully utilized, just like a memory interleaving. Network interleaving has a different granularity. Different interleaving granularity has different performance characteristics and different requirements on hardware. The fine-grained interleaving is to distribute the packet of a message to multiple physical interfaces of an abstract interface one by one. It has the highest bandwidth utilization, but extra hardware overhead. The coarse-grained interleaving is to distribute packets in a more coarse-grained way. It is implement-friendly and can reduce power consumption under low network load. To evaluate the network performance, we design a chiplet-specific circle-accurate C++ simulator. The router model of the simulator is based on typical virtual channel router. The switching technology is based on virtual cut-through. It contains a pipeline of four stages: routing, VC allocation, switch allocation, and transmission. The crossbar is primitively scheduled, and the starvation is avoided through the first-come, first-served strategy. Flow control is based on credit, and each output port can know the occupation of the corresponding input buffer. The cross-chiplet VC allocation and the cross-chiplet message transmission stage consume more clock cycles. Our simulation allows non-uniform link configurations to reflect the different properties inside and outside the chiplet. Each port's bandwidth, latency, and buffer size can be configured individually. It can also introduce longer delays for the cross-chiplet pipeline stages. The simulator's default parameters used in the following experiments are shown in the table. We evaluate our method on 6 different traffic patterns. The baseline is a dimensional order-based adaptive routing on 2D mesh. As shown in the figure, for all traffic patterns, our method has a significant latency advantage over traditional adaptive routing in 2D mesh. Our minus first routing on HyperCube has a saturation injection rate of more than double at all traffic patterns. 3D mesh has an advantage at some patterns such as bit reverse. The evaluation results show that our method can provide a better interconnection scheme than 2D mesh for various traffic loads. Our methodology has a great advantage on the traffic with mass global communications. That's all. Thank you for listening.